Okay, here we go. So, periodicity and the periodic table, most of which is fairly straightforward, but some of which I will try very hard to explain in the way that I explain it, in the hope that it makes it easier. Okay, this is, as it says, the syllabus is enormous. It looks enormous, and part of my way of doing things with students is not to show them something like this. It's really important that you know that this is what might be asked, but you need to become, I'm not expecting you to read that, it's too small. It's basically saying that it's about group 1, group 2, group 7, group 8 or 0, and the properties across the period. Now, if you become familiar with the examinations, you will know that there are more questions asked about the trends across a period than there are about, for instance, group 2. So I don't show this to my students. What I try and do is to simplify things. And sometimes we think we are simplifying things. For instance, we put all the chemistry of sulfur together on one piece of paper, and we think that's great. Now we've got it all there. That is not simplifying things. That is making things far more scary and far more complicated. Now, we might want to have this as a note which we can teach from, but it is too horrible. So we must not give students things like this unless it is right at the end. So let's get back to the periodic table, and we're going to simplify things. Here is the periodic table. You will be very familiar with the periodic table. Well, you may be, or maybe you're not, because there are lots of different kinds of periodic table, and you may have come across them. This one here starts up in hydrogen here, helium, lithium, beryllium goes round, boron, carbon, nitrogen, oxygen, neon, sodium, magnesium, delta, aluminium, following the yellow band. This is because this is a model for producing a cone-shaped periodic table. This one, oh my gosh, what? Hydrogen, helium, lithium, beryllium. Ah, look, it's a spiral. Now that's sensible, because when we look at our normal one, we don't make the students aware that it goes sodium, magnesium, aluminium, silicon, phosphorus, sulfur, chlorine, argon, and next to argon is potassium. We don't make them see that, which is why sometimes producing one of these and keeping it in your teaching room is quite useful. But there are lots of different kinds. This is my favorite. This is another spiral one where it goes hydrogen, helium, lithium, beryllium, and then boron, carbon, nitrogen, oxygen, fluorine, and so on. So it just winds round, okay? Some of them confuse me. I don't know why they would want to do this. It's about quantities, actually, but that's not important. Here, this one's got a nice picture of Dmitry behind it, the Russian who came up with this, though actually some other people came up with it as well. So we're going to use this one. And I'm going to go through, I'm not going to explain most of it, because you're going to get this as a resource. So here we are. So firstly, they need to know the organization of it, which you know, and they just need to have this shown to them, very, very straightforward sense. Okay, they've got to know what the groups are, they've got to know what the periods are, they should know why it's called periods. They should know that because periodically we come back to the same place, like on the spiral periodic table, that there are around about 120 elements. Of course, you know, whether we talk about naturally occurring elements or ones which are made artificially, doesn't matter. We're just talking just over 100. Most of them are metals. Some are metalloids, and then most of the rest are non-metals, but the vast majority are metals because they don't get that most of the time. Okay, the groups which we need to know about are the alkali metals, the alkaline earth metals, the halogens, and the noble gases, and those are their standard numbers. Though if you're working from an American table, and increasingly Other countries are using it as well. You might find this is number 1, this is number 2, that's number 17, and that's number 18. Don't worry about it. In many ways, it's much more use for us to use 1, 2, 7, and 8 because that coincides with the number of electrons in the outermost shell, which is comforting to students. So the basics. Students need to be able to do electronic arrangement. Just mainly so they can place something in the periodic table, or in those questions where they get an X in a blank periodic table, they can look at the group and they can understand what it is. And they need to know the electronic arrangement for the sodium period, what I call Namgal-Sipsklar, because if you write them out in order, it becomes Namgal-Sipsklar, Namgalsi, etc. So we would normally just use 281. We wouldn't use 1s2, 2s2, 2p6, 3s1, or anything like that. And they have to be able to predict the ionic electron arrangement, because look at this, it has 1 in the outermost shell, and therefore it's going to lose that 1, and it's going to become 1 plus, and therefore 28, and so on. They need to be able to do that. Give them plenty of practice doing that. You may be lucky enough to have a decent practical laboratory. Many of you will not. Don't worry about that. I know that Challenge 8 is trying to make some laboratory time available, but there are really good videos, and some of them we might have time to look at today, and some of them we won't. It doesn't matter, because there are many ones on this particular presentation. Group 1. So what I do is I do this. I say, okay, I'm going to run through physical properties, and then I'm going to run through chemical properties. And I explain from the periodic table some things before I start getting into the groups. So I talk about atomic radius and so on. I start doing the periodicity before I look at group 1, group 2, group 7, and so on, unless I have a laboratory. If I have a laboratory, then I will start by making the students excited by looking at group 1 on water. But the properties we have to be able to explain, and your way through their understanding is to tell them a property and then explain it. Okay, so they need to know the property and the explanation. So group 1, good conductors of electricity, yes. Oh, they've got delocalized electrons. Okay, fine. They're soft because they're big atoms and their metallic bonding is weak. They are shiny when they're cut, but because they're very reactive, they tarnish very quickly, they float on water, etc. So you need to give them the explanation as well as the property. In the reactivity, in the chemical properties, it's pretty obvious, and you can ask them to explain. Once you've been through why something might lose or gain electrons, they may easily be able to go, oh, well, group 1, ask them, what do they need to do? They need to lose 1 electron. Okay. And they're the biggest atoms of their period. Okay. So it's going to be easy to lose that electron. Aha. It gets bigger. They become more reactive down the group. Oh, because they're getting bigger. They're still only losing 1 electron, but going down the group each time there's a new shell. I see. And they react with water because they're higher than hydrogen in the electrochemical or reactivity series, and etc. Now, if I try and pick this up, it won't play, but these are 3 hyperlinked sets of experiments which you can show to your classes if you wish to. This one is quite good. This is in a laboratory. I'm encouraging you to look at this later. I think they're just a bit silly, but they are quite useful. Okay, so these are ones that you can use with a class, particularly if you do not have a laboratory. So then we go on to group 2. I know I'm going quickly, but it's because it's all here. I just want you to understand how I would do it. So I would isolate it: beryllium, magnesium, calcium, strontium, barium, radium. So beryllium, we're not going to come across beryllium because it's super toxic and there's only a small amount of it and it's very expensive. But in your laboratory, you probably will come across magnesium and calcium. You may have some strontium. You're unlikely to have any barium, but you can do really good experiments with magnesium and calcium with water to illustrate the reactivity series in the group, the fact that as you go down, they get more reactive. And you can also show that they are much harder than the group 1 metals. So I normally say this is a slightly less interesting group. And I say, why could they be a little bit less interesting? And think of their reactivity. And most of the students will be able to, after a short time, to go, okay, they've got to lose 2 electrons. That's more difficult. Don't ever allow your calcium and acid to come together. So we've got slightly different physical properties because they're smaller atoms and they have better metallic bonding, so they're harder. It's very difficult to cut a piece of calcium. It's very, very easy to cut a piece of potassium or sodium. So there's a couple, sorry, whoops. There's a quite a good set of reactions here. It's fairly simple. It's time for another teaching idea. I said right at the beginning that I don't want people to teach and look at lots of examination stuff on the way through. But when you get to the end of a topic, I suggest that the students are asked to come up with some revision material which is really, really brief. And then that is collected together. We can use some past examination questions and answers to see how they ask about that topic. We can use pictures. A lot of students remember pictures, which is why things like the moles and so on. We don't wait right until the end. Otherwise, we spend a lot of time producing revision notes and not using them. And you can take the class and divide it up and say, okay, we have just finished moles. I would like the group in the table by the window to produce the revision material for this. And they should be limited, so they only produce very, very brief results. Then you keep them, and then at the end of the course, you bring them out and stick them on a wall, and there we have our revision materials. Okay, here's group 7: fluorine, chlorine, bromine, iodine, astatine. Fluorine, extremely mean. I have used fluorine. It is really quite difficult to use because it eats through many of the things you put it in. But it is not true that it eats out its way out of everything. It will eat its way out of glass, but it won't eat its way out of nickel, for instance, because nickel reacts with fluorine and it forms nickel fluoride, which then is impervious. It won't eat its way out of Teflon, non-stick saucepan material, because it is already fluoridated, etc. Most people have come across chlorine because of swimming pools. They may have come across iodine because tincture of iodine, a solution which is used in wounds. Physical properties are really important in the halogens. You need to know why they are low melting point and boiling point, and therefore gas, gas, liquid, solid. Gas, gas, liquid, solid going down the group. And you need to know that they are only held together by very weak, they are molecular, so they are simple covalent, just diatomic molecules held together by weak van der Waals forces. Now, because van der Waals forces depend on the number of electrons per molecule, it's proportional to the number of electrons. So as you go down, fluorine number 9 has 18 electrons per F2. Chlorine number 17 has 34, basically twice as many. So twice as powerful a force. Get the idea? So you can go down, bromine number 35, so 70 electrons in the Br2 molecule, and therefore it's a much more powerful force of attraction between Br2 and Br2 than it is between F2 and F2, and therefore gas, liquid, solid. They know about the characteristic smells. You can look like you can speak Greek because bromine comes from bromos, which means stench or really bad smell. And they need to know the colors. They also then need to know about the chemical properties. And again, if you have done electronic arrangements properly, the fact that they know that they only need one means that they will be the most reactive nonmetals. And they may then assume that as you go down the group, they get more reactive, just like group 1. But that's not true, because it's much easier to steal an electron from something if you're very small and you can get your nucleus close to it than if you are huge. So the outermost electrons in iodine are a very long way from the nucleus. So the nucleus, although it has a lot of protons, will not pull an electron as well as fluorine. So the smaller atoms are better. And the last bit is all about the reaction with metals and that they make them into the highest valency or oxidation state possible. Like iron will form with chlorine, will form FeCl3, not FeCl2. If you want to make FeCl2, you would have to react it with hydrochloric acid. And they dissolve in water, forming bleaches and acids. Here, again, are some reactions which you can look at. They're really good. They are very good little, I've just selected. You can search very easily, particularly on YouTube. There are many, many good videos, but you need to watch them before you, if you have the ability to show it to a class, you need to watch it first in case in the middle somebody suddenly takes their clothes off. I know that sounds unlikely, but I found a video. I'm not going to tell you what it was about, but it was chemistry. And in the middle of the video, suddenly there was a picture of a man and a woman with no clothes on. And I went, thank goodness I did not show that to children. So you need to watch the videos first. It's a really simple idea, but you need to do it. Group 8, helium, neon, argon, krypton, xenon, radon. In the UK, we have a problem with radon. Radon is trapped by very dense rocks like granite, and it comes up underneath the houses. And because it is freezing and horrible here in weather, quite often we keep our windows closed, and this builds up and it causes cancer of the lungs. So you only really need to know a very simple bit about these, that because they are monatomic molecules, in other words, single atoms, they only have very weak van der Waals forces, which means they're all gases. But they become more and more dense. They are very unreactive because they've got full shells, and that means that they can be used in many things. And here are a couple of videos which you can use for them. Then periodic properties, I'm going to use a group of graphs, and you will see why this is important. So show your students, get them to know the order, make it into a word. Nam gal sips klar. Nam gal sips klar. Silly word, but it helps them know it. Here they are. Always talk them through, get them to produce their own electronic configurations, get them to try and think which are metals, which ones are non-metals, help them, and their structure. And then here briefly are the trends. This will take only a few minutes. Atomic radius. Now this surprises people. This is in the periodic table. The atomic size increases down the group. That is no surprise. But the atomic size decreases across a period. And you will know that is because the electrons are all going in one period, are going into the same shell, but we are getting more and more protons. So 3 protons, 4 protons, that's a 33% increase in the number of protons. Yeah, 3, 4, 5, 6, 11, 12, 13, that's a 10% increase from there to there, okay? So that as we go across, the outermost electron, 281, 282, 283, 284, they're all going into the third shell, but more and more protons, 11, 12, 13, and so they get smaller. So there's the atomic radius. It gets less important towards the end. In fact, if you are looking at atomic volume, you will find that in many graphs it shows argon as being bigger. That's not true. It is bigger per mole. Don't worry about that. Just tell your students it does this. Ionization energy. This is more complicated than you need it to be. You will probably be familiar with this. 2 up, 1 down, 2 up, 1 down, 2 up across a period. But your students really need to know up. And that's because across the period, the atoms get smaller. So to lose 1 electron from each one of them, here it's easy, bit more difficult, more difficult, more difficult, more difficult, and therefore the graph goes up. You will probably know that aluminium has it slightly lower than magnesium because it is into a p subshell. That sulfur is slightly lower than phosphorus because the p subshell, the 3 subshells have 1, 2, 3, 4 electrons in, and therefore it is paired. This is too complicated for your students, this bit. Just remember it can be basically a straight line. But these two you should know in case somebody shows you it. So this is S1, S2, S2P1, P1 slightly higher, P2, P3, P4, paired electron. They repel each other and therefore they are higher energy, therefore easier to lose. P5, P6. Melting point and boiling point. Very simple. The first 3 are metals, and this is melting point. You will see something different with boiling point. Weak metallic bonding, better metallic bonding, better metallic bonding. So how come aluminium is about the same as magnesium? That is because aluminium is packed less well. So these are all metallic, these 3. Silicon is like diamond, like carbon in diamond. It forms tetrahedral, giant covalent. These guys are all simple molecular, simple covalent, and the lowest is argon because argon goes around on its own, chlorine goes around as Cl2, phosphorus as P4, and sulfur as S8. So remember, van der Waals depends on number of electrons. Number of electrons, 18 for argon. Chlorine, 17, but goes around as Cl2, so 34. Phosphorus is number 15, but goes around as P4, so that's 60 electrons. And then sulfur goes around in rings of 8. So metallic, 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 giant covalent like diamond, and simple. If you look at boiling points, you get what we really expect across groups, that they continue up to the high point of group 4 and then drop straight back down. Electrical conductivity, there is a table, metallic, metallic, metallic. Better and better and better because more electrons in the delocalized sea of electrons. Silicon, they're all locked up, so it's a poor conductor, and these guys, they're completely locked up, so they are not conductors. So there it is. Good, better, best, not very good, rubbish. Finally, thermal conductivity. Thermal conductivity is shown in this quite easily as a set of colors. Really good conductors up at the red end, really poor at the blue end. So thermal conductivity across the period, quite good, slightly better, better still, not quite as good, and very poor. Okay, so that's what thermal conductivity shows you. Okay, I'm going to stop because this bit here, I want to be able to show you this particular periodic table, which I will do after lunch. So now I believe it is time for your lunch. Am I right? It's time for lunch. Is it time for lunch? Oh no, they've all gone to sleep. Even Mathari with their biscuits. Kibera, is it time for lunch? Well done, Wamini. Well done, Gillen. Well done. Well done, Teacher Wycliffe, Teacher Gillen. Well done. Okay, guys. So I think we're back in an hour, which will mean for you 2 o'clock. I hope they've given you some good ugali. I hope they've given you something good to eat, and it's warm because it's cold outside. But you need to do some brain gym and some stomach gym and some move around and talk to people and have fun. Okay, so I'll see you in an hour. Bye-bye.
Bye bye.